gas laws. Hopefully you've gone through and answered the questions at the end of the last video, and now we'll go through this in a bit more detail. So our goals will be to learn how parameters such as temperature, volume, number of particles, and pressure are related to each other. We'll then answer some conceptual questions about what occurs when one parameter is adjusted while the others are held constant. First, let's talk about Boyle's law. This assumes that temperature in moles are constant. So we're not changing the temperature and we're not changing the number of atoms of the gas. And it relates pressure to volume. If you increase the volume, what would happen to the pressure? You can see as this number goes up, this number goes down. So if you increase the volume, you decrease the pressure. Similarly, if you decrease the volume, if you make this smaller, the pressure increases. And again, this is only true when moles of gas and temperature are held constant. Otherwise, you'll have to factor in those changes as well. Let's look at a graph of what this would look like. These graphs are something that you should be able to replicate if I were to ask you to, or match. So as pressure and volume change, you can see as we change volume, you get this 1/, line. Now, because it's always nice to have straight lines when we're trying to work with equations and graphs and things like that, if we look back at what we have here, we can see that if we were to compare pressure and 1/v, we'd actually have a straight line. And so we can do this and put 1/v on our x-axis, or excuse me, 1/v on our x-axis, p on our y-axis, and see that we get a straight line. Now let's do Avogadro's law. Avogadro, we best know him for Avogadro's number and talking about the relation between moles and number of atoms. And this is going to make a lot of sense with what his law is named after. This discusses the number of particles and how that relates to volume. So this relates moles to volume. As the number of moles increases, the volume increases. And if you think about this in terms of balloons, think about what happens if you put one breath of air into a balloon and how the size of that. Now add another breath. What did you just do by adding another breath into the balloon? Well, you added more moles of gas and your volume increased. This is true when pressure and temperature are held constant. So if you have something that is holding pressure relatively constant and your temperature isn't changing, Avogadro's law will work. Otherwise, you have to take the others into account as well. Now let's do Charles and Gay-Lussac's law. So this relates temperature to volume and temperature to pressure. So as temperature increases, volume is going to increase. As temperature decreases, volume is going to decrease. And then if we look at the other side of this, and if we keep a constant volume and we're changing our pressure, as temperature increases, pressure increases. And as temperature decreases, pressure decreases. And one of the places that we think about this happening is if you've ever been camping and you slept on an air mattress that you filled during the daytime, by the middle of the night, it's pretty flat. And that's because the gas inside has exerting less pressure on the air mattress, and so therefore it's not holding it up quite as well. Same thing with tires. This is why if you were to fill tires on a very, very cold day to maximum pressure, once they started heating up from driving or it got warm out, you would risk bursting your tire. So here's some graphs dealing with Charles's law. And the same type of graph would be true for pressure. So as temperature increases, volume increases. So we get a nice positive sloped increasing line. So this is the sort of general sketch of this. But it's good to know what's going to happen if you have different pressures and how these would compare. Now over here, we have a graph where we have changed our pressures. So as your pressure increases this direction, at a given temperature, you can see how this is related to each of the pressures, where our lowest pressure shown here is 0.5 atmospheres, and our highest pressure is 4 atm. So now we're going to go over some conceptual examples and get the hang of this before we go on to the math. So first of all, we have a sturdy, rigid container. Since it's sturdy and rigid, the volume isn't going to be changing. And now we double the number of moles of atoms. So since the volume can't change and the temperature isn't changing, if we double the moles of atoms, we're doubling how much these atoms how much these atoms collide and how much pressure is exerted on the system. And so therefore the pressure is going to double. Now, keep in mind, you can always pause this video, and I would highly suggest that you do so and think about the answers before I give them to you. So here, if the temperature of a rigid container is decreased, so again, we have a set volume, but now we're changing the temperature. What's going to happen to the pressure? Since we have this sturdy container that isn't going to change volume, and we are lowering the temperature, our pressure must decrease. Now, if a system with a container and a movable piston is heated, so what I mean by movable piston is in like some of those pictures that were in previous slides. This piston can move up and down depending on the pressure that is exerted upon it. So, if we have a system in a container, a movable piston, meaning volume can change, what's going to happen to the movable piston? It's heated, so because it's heated, we're going to have more pressure exerted on that piston head, and therefore it's going to move upwards in order to resist this change in pressure. So it will move as so to increase the volume. Now if the container volume of a given sample is doubled, so now we're taking a sample and we're putting it into a container which is double the size. So maybe we've expanded the container out, maybe we've given it a new container, maybe we've attached a container of the same size to it and let it go in between both, something of that sort. We've doubled the volume. The temperature is also doubled. What happens to the pressure? So now we have two things going on. We're doubling the volume, which means that we're halving the pressure. But at the same time, we're also heating it up, which is going to increase the temperature, or increase the pressure. So because we're both increasing the pressure by half on one step, and then decreasing the pressure by half on the other step, it stays the same. Now in this next case, we're changing two things. We're doubling the volume, and we're also doubling the temperature. Now, if we think about what would happen if we just doubled the volume, that would half the pressure because we're giving it more room. So that would half the pressure. But at the same time, we're changing the temperature. Now, if we were only to double the temperature, that would double the pressure. So in one case, we're halving the pressure. In one case, we're doubling the pressure. And since we're going to do both to it, that means that overall it stays the same. Now, we have learned how parameters such as temperature, volume, number of particles, and pressure are related to each other. And we've been able to answer some conceptual questions about what occurs when one parameter is adjusted while the other are held constant. And by talking about this doubling, we're starting to get into the idea of real numbers and real math here as well, which we'll move into in the next podcast. Now, before moving on, either in the videos or coming to class, I want you to think about something for me. I want you to think about how we can combine all of these parameters, pressure, volume, temperature, and moles, so that we can accurately calculate changes in multiple variables. What happens if nothing is held constant? What happens if we're changing pressure, volume, temperature, and moles? How would we combine all of this into one equation that works out so that we can do this? And think about that very last question on the last slide if that helps you out. So, hint, look at what's proportional to each other and set them on opposite sides. And then check to see that your units cancel. And if maybe you've heard of this equation before, most of you have had some high school chem, and you may know where I'm kind of leading you into with this. But it'd be good if you could also kind of see how this is derived from each of these laws that we've talked about